this problem dealing with projectiles is a fairly straightforward one, except for one little trick that we have to watch for at the end. So we're just going to read through the problem here and plug into the formula to begin with. Projectile sent off with initial velocity v0 350 and clears a fence 3,000 meters away, so that 3,000 meters is going to be our d value. Height of the fence is the same height if the distance of projectile traveled is given by that formula. Find the interval of possible launch angles. So that tells us there's going to be some interval that this launch angle is going to be between. That's going to be the little trick that we need to look at the end here. So plug in our values. 3,000 equals v naught, which is 350 squared sine 2 theta over 9.8. So if we take that and solve for the sine of 2 theta, we have 3,000 times 9.8 divided by 350 squared equals the sine of 2 theta. Okay, so taking the inverse sine of each side, we have the inverse sine of 3,000 times 9.8 over 350 squared equals 2 theta. Now this is where the little trick comes in, because typically you would think, oh well, we just divide each side by 2 to get theta, but that's not the case here. For this one, we actually want to solve the inverse sine first, and the fact that it equals 2 theta means that it really can be in the first or second quadrant, because with 2 theta being in the first or second quadrant, that keeps theta in the first quadrant. So just a little trick there. So if we solve that for 2 theta, we get the 2 theta is approximately 13.9. Well, that's really only half of what we want. It's really between that 13.9. I don't know why I wrote 2.9 there. 13.9 and its complement. Because if the 13.9 is here, then we look at a reference angle over here of 13.9 also, which would be approximately 166.1 degrees. So it's between that and 166.1. And now all we have to do is take and divide that by 2 to get the final answer of approximately 7 to 83 degrees.